Hello and welcome to our second video. Finishing up a little bit about proton NMR, I'm noting that coupling leads to splitting. Splitting is the observed signal in the spectrum. So the phenomenon of coupling leads to that. When we're defining what the spectra signals look like, we talk about multiplicities like singlet, doublet, triplet, multiplet. So when you're reporting data, report them as you see them, not as you think they should be. So you're saying to yourself, you think a signal should be a triplet, but you can't really make out the three peaks of the triplet. You might have to call it a multiplet. Okay, basics of splitting we've talked a little bit about already. Equivalence before splitting, remember? Those three protons are equivalent. There are no neighboring hydrogens at this carbon, so those remain a three-hydrogen singlet, S. These are a three-hydrogen doublet because that single signal is split once by a neighboring hydrogen into two lines total, or a doublet. Three lines are generated when there's two neighboring hydrogens to split that three-hydrogen signal. This is a three-hydrogen triplet then. If we have an extended system like you see here, this still is the same. Three hydrogens split two more times into a triplet, but these two protons here are equivalent to each other. They generate a two-hydrogen signal, split 1, 2, 3, 4, 5 additional times, resulting in 6 lines total, or a sextet. And then these two protons here would be a triplet because two hydrogen signals split 2 additional times. When you're determining the splitting on a neighbor, you treat each proton as an individual. When you're determining the splitting of those same protons themselves, you treat them as equivalent, if they're equivalent. Now there's a few exceptions. Aldehyde protons, like you see here, are often not split, almost never split, in fact. The carbonyl forms some sort of barrier to coupling, even though you think it ought to split. OH and NH protons are sometimes split, sometimes not. They're usually broadened. And so with these two, it's sort of a case-by-case thing. Sometimes they are split, sometimes not. Often, I would say, not split. Onward to carbon-13 Nmr spectroscopy. We're lucky in proton NMR that the most abundant isotope is the one that's also visible in the proton NMR spectrometer. That's not the case with carbon. The visible isotope of carbon for NMR is the less abundant, although, as it turns out, it's just abundant enough to see carbon-13s represented in all the atoms of a molecule in a mixture because there's so many molecules in that mixture. Now there is actually coupling between carbons and their attached protons and carbons and neighboring protons, but as far as what you would see in a coupled carbon-13 NMR spectrum, you would see the multiplicity, say, of this carbon right here as being a signal split 2 additional times by its attached protons, resulting in a triplet. This carbon right here, you would see a single signal split 3 additional times into a quartet for that carbon. You would think that this information is useful. Actually, it is very useful, but not in a carbon-13 spectrum because of the amount of peak overlap that is going to get generated in a carbon NMR. The beauty of a carbon NMR is the resolution And remember, organic molecules are mostly made of carbon skeleton frameworks. So the normal carbon-13 NMR is decoupled. The coupling data is subtracted out, but it still exists, and we're going to actually revisit that very soon. We're going to make use of that because the data is buried in there. In a decoupled carbon-13 NMR, that's like the carbon NMRs you've always seen, where every carbon, no matter what it is a singlet. And a very fine singlet at that, almost a straight line. But they are peaks if you zoom in on them. General chemical shift trends in carbon NMR, they're very similar to the proton NMR trends. One thing is that methyls progressing to methylenes and methynes, useful terms for those, you see a progressively deshielding effect. So all things equal, the CH is going to be much more deshielded than the methyl. Heteroatoms attached to carbon, if the carbons are not unsaturated further, like a double bond, are in this region very characteristically. So alcohols and amines. A carbon with 2 oxygens very characteristically is, and as we would expect, much more deshielded, around 100. Aromatics and alkenes are in the aromatic region, about 110 to 140. An oxygenated aromatic carbon is often very deshielded, more like around 150, 160. Because when you think about it, it's almost like a carbonyl, right? A double bonded carbon with an oxygen on it. Carbonyls are among the most deshielded things. If you have amides, esters, carboxylic acids, the distribution of electrons is among the 3 atoms here, for example. That has a little bit of a shielding effect compared to aldehydes and ketone carbonyls. Ketones are very deshielded. So this region of the spectrum is especially useful. If we go down here, and this is from your table that's posted, the carbonyl region. And I'm going to assume that no one needs to really review, but if you do need to review your functional groups, I would do that immediately. It's very important to recognize ketones, aldehydes, carboxylic acids, esters, amides. It's likely we're not going to see very many thioketones. So everything above, let's say 170 for sure, is very likely a carbonyl. Notice how distinctive ketones are. If it's over 200, it's a ketone. If it's around 190, typically it's an aldehyde almost always. Probably not a thioketone. Acids, esters, amides really float around the 170s. And remember, like 160 could still be an aromatic oxygenated carbon. But definitely use this portion of the table every time you think you might have a carbonyl because it's extremely distinctive. I would prefer this vastly over IR. Over here on the right, we have a few other hand-waving little things. So the relative height of peaks, for example, a methyl here is going to be a little bit taller. They seem to absorb, just resonate a little bit stronger. Your average sort of peaks are here. If you see a peak that's clearly doubled, and we often see them in the aromatic region, this might be a case of a paradise substituted aromatic where these 2 hydrogens are equivalent, therefore these 2 carbons are equivalent, and giving you a 2-carbon signal, 2 equivalent carbons here and here, for example. If they're very short, they're often quaternary carbons. and the more deshielded one could very well be a quaternary carbon, like a carbonyl. All right, so just a little bit of, you can't be 100% sure that if it's taller or shorter, it's one or the other, but some very strong differences, you can assume that in your problem solving, for a while at least.